In the name of God, Farsi, a Persian Semantic Textual Similarity and Natural Language Inference Dataset. In this presentation, I want to talk about introduction of Farsi, Semantic Textual Similarity and Natural Language Inference tasks, related works and available datasets, description of our dataset and its statistic, methods that tested and results of them, and finally conclusion of our paper. Semantic textual similarity measures the similarity of two pieces of input text using a measurement criterion. It is a measure that examines the similarity between different levels of text such as words, sentences, and documents semantically. Natural language inference task classifies a pair of premise and hypothesis sentences into three classes: contradiction, neutral, and entailment. It is an important step towards natural language understanding. Recognizing similar sentences and paragraphs in terms of meaning and concept has an important role in natural language processing, such as information retrieval, text classification, subject extraction, text summarization, machine translation, and plagiarism detection. Supervised methods, such as deep neural networks, require a lot of labeled data. In NLI and especially in STS tasks, it is impossible to train or evaluate deep neural networks without appropriate datasets. Lack of appropriate datasets in the Persian language is a major obstacle to progress in this area. Therefore, we decided to gather Persian labeled data. For this purpose, to ensure the quality of the dataset and test with the existing method in English, a translation of the stick dataset has been used. You can see some of available datasets for semantic textual similarity tasks in English. MRTC. The Microsoft Research Paraphrase Corpus is a text file with positive and negative samples. Quora question pairs contains more than 400,000 pairs of questions about Quora. STS. Similar Semantic Textual Similarity. The STS benchmark consists of a collection of English datasets organized in STS semantic evaluation tasks. SEEK. Sentences involving compositional knowledge dataset. In this data, each pair of sentences is annotated with one of the three labels: neutral, entailment, and contradiction, as a description for the semantic relationship between the two sentences, and is scored with a number between 1 and 5. And then there are some of available datasets for natural language inference tasks in English. SNLI. The Stanford Natural Language Inference Corpus is a collection of labeled English sentence pairs written by humans. This set is used for classification with the labels of contradiction, entailment, and neutral. The next is SEEK, and that I said before. And next one is Cited. This set includes samples with entailment and neutral labels. You can see the only available dataset for natural language inference tasks in Persian. It contains samples with contradiction, entailment, and neutral labels used for the task of natural language inference in Persian. There is no more NLI dataset, and also there is not any STS dataset in the Persian language. We need a high quality dataset to be able to trust the results obtained from it. Therefore, to achieve this, we decided to translate and edit a valid English dataset. Finally, we chose the SEEK dataset. We had many challenges to translate sentences from English language to Persian language. For example, some grammars in English did not exist in some cases for Persian. Some words in English had almost the same letters but had different meanings, while their translation in Persian was words with completely different letters. The translation of some words from English to Persian language had exactly the same meaning. Therefore, we try to use their synonyms with different words or phrases. The language power of English is high, so some words did not have Persian equivalents, and we edited the sentences and wrote them in other words. These changes were to the extent that they did not lead to change in their labels. The table shows examples of our dataset. These are in a .txt format. It has 6 columns including the ID of sentences pair, the first sentence, the second sentence, the relatedness scores of each sentence pair, the entailment label, and a binary label that means the similarity or dissimilarity of the sentence pair. The binary label includes 0 or 1. We create this label ourselves so that it can be used to train two-class models as well. The relatedness score is a number between 1 to 5. It's used for SDS tests. If the score of two sentences is higher, they are more similar. The entailment label is used for NLI tests. It includes entailment label for sentences that are inferred from each other, contradiction for sentences that have contradictory concepts, and neutral label for sentence pairs that there is not any correlation between the concepts. This data consists of about 10,000 sentence pairs. Minimum sentence length is 2 and maximum is 35 tokens. This shows the statistical information of the introduced dataset. And the figure shows number of sentences based on number of tokens in them. Train, trial, and test subsets have almost the same distribution. In this section, some of the best available approaches to find semantic similarity and natural language inference will be discussed. These approaches include traditional statistical and deep learning models. We use different pre-trained embedding, word-to-word, glove, fast-text, and BERT sentence transformers. So I want to introduce word embedding methods. Word-to-word is a method to represent words in a n-dimensional space. It is a two-layer neural network that its input is a text and output is the word vectors of that text. There are two main ways to train a neural network in the word-to-word model. CBOW, Continuous Bag of Word Model. In this method, the model tries to guess the desired word using the words around a word. The next is skipgram. This model is in contrast to the CBOW method. That is, the model tries to guess the word around a word that receives it. Glove. This method is unsupervised, same as the word-to-word method. The only difference in this method is how to calculate the values of each vector. In this method, the number of repetition of each word in the whole text is calculated and it is checked in which subject each word is used more. Fast-text is a method that represents each word as an n-gram of characters. N-gram feature is the most significant improvement in fast-text, because rare words can be broken down into n-grams to get their embedding. It is the key difference between fast-text and word-to-word. It is a good solution for out-of-vocabulary issue. Convolutional neural network is one of the methods that we use to test Farsi. This architecture provides an overview of model that we use. After pre-processing, each pair of sentences is given to the convolutional neural network as embedded vectors of their words. Then, the CNN describes and combines the word vectors from each sentence into an appropriate sentence-level embedding. After that, the convolutional neural network, by weighting the combination of these vectors, constructs an embedding vector at the sentence level for each of these sentences. Then, the distance between two vectors is obtained by multiplying and differentiating them as a vector of semantic difference. When a fully connected neural network, FCNN, transfers the semantic difference vector to a probability distribution over similarity scores. The next method is CMS by LSTM, especially Manhattan by LSTM. This architecture provides an overview of model that we use. There are two networks, LSTM-A and LSTM-B, which each process one of the sentences in a given page. It focuses on CMS architecture with tied weights such as that LSTM-A equal LSTM-B in this way. CMS networks consisting of the LSTM network are used to compare data in pairs of labeled sequences. For this purpose, we give embedded word vectors aligned with information to LSTM networks to encode the meaning expressed in the sentence into a vector of fixed size. Finally, after encoding each sentence with an embedding vector, the distance between the two vectors is calculated and the final label is out. In the structure of the BERT method, a transformer is used. Transformer is a new method of converting text to a vector that uses only a simple neural network and attention mechanism. In this architecture, pairs of sentences are converted to the vectors by pre-trained BERT models, and the similarity vector is given to them as input to the LSTM network. After applying the pulling and drop of layers, the output of a fully connected layer with 3 neurons determines the degree of similarity of each pair of sentences. In this method, the BERT model is first frozen and the layers added on the data. Then the whole model is fine-tuned with a very low learning rate. You can see architecture for sentence pair classification test. We prepared about 10,000 Persian sentence pairs in the data collection phase. We use this data separately for both STS and NLI tasks. These methods that we use and their results in the semantic textual similarity test are shown here. Each of the methods with using 4 types of pre-trained word embedding that introduced in the previous section. In this task, we use a score similarities label for each sentence pair. In this case, the Pearson evaluation criterion is used. In the CPOW model, word embedding plays a significant role in the final result. Because word embedding averaging is used, so the more meaningful the word embedding is, the better the end result. Fast-text embedding greatly increases the final accuracy due to its greater power in recognizing unknown words. The USIF model is relatively similar to the CPOW model, except that it uses words frequency to give a higher coefficient to words with a higher probability of occurrence, and uses a weighted average. So, this is a significant improvement vs when the CPOW model did just a simple averaging. This method is unsupervised. In this method, the results of different embedding show that fast-text is more accurate for the same reasons mentioned above. The best result obtained for CNN classifier with fast-text pre-trained word embedding model as input. In general, the accuracy of this classification is higher than other methods, and this shows the superiority of a deep learning method vs the USIF unsupervised method and the CPOW supervised method. In this task, we use entailment label for each sentence pair. In this case, the accuracy evaluation criterion is used. We train a method as three-class problems. In this task, we use Siamese by LSTM at first. It is one of the most common methods in this field. In this method, the result of using different embeddings shows that fast text is more accurate. The next model is CNN that works better from Siamese by LSTM. It is same as CNN that used in SCS test, except that it has 3 classes instead of 5. The best accuracy is obtained by fine-tuning pre-trained BERT model and adding by LSTM on the top of it. This shows the superiority of transformers with the other architectures. Bidirectional LSTM is trained both from right to left to predict in the next word and left to right to predict the previous word. But in BERT, the model is made to learn from words in all positions, meaning the entire sentence. We fine-tuned the pre-trained model with just 2 epochs. Conclusion. We introduced the first relatively large-scale STS dataset and the second NLI dataset for Persian language and presented the dataset statistic. This data is published for free in GitHub. In order to ensure the efficiency of the data, this dataset is collected by translating and editing the sentences of SIG dataset. We tested different models of semantic similarity and natural language inference on it. This method includes some traditional and state-of-the-art models. The accuracy obtained indicates the quality assurance of the prepared dataset. This paper is the basis for further Persian language research in the field of semantic similarity and natural language inference. Thanks for your attention.